Hello everyone and welcome back to Minic Analytics. I'm very glad to have you back. In this video, we are going to be discussing yet another supervised learning algorithm. For this case, it will be the XGBoost, and we are going to be using the same in fakemoney classification. Before we get started, please consider subscribing to our YouTube channel. We are welcoming you to our wonderful community. You can also hit that notification bell so that you never miss any of our video updates. And once again, thank you for joining me today. And without further ado, let's get started. So for this analysis, we will start by importing the Python libraries. So I've imported the NumPy, Pandas, Matplotlib, as well as the Seaborn libraries. So for each library, you can just, for example, when you want to import the Pandas library, you can do this by typing import pandas as PD. And this, by typing this line of code, you'll be importing the matplotlib library, and this one will be for the Seaborn library. So after importing the libraries, we will then move ahead to load our dataset onto our Jupyter notebook. My file is a CSV file, so I use the read CSV function. So when I run when I execute this line of code using the head method, so basically I just want to print the first 5 rows of the data frame. When I execute that, you can see that the output is our data frame, and from that you can see the columns as well as the values in the respective columns. So basically that's how you can do that. So moving on, in the next step, we'll be inspecting the shape of our data frame. So for the shape of our data frame, I'm going to use the info method. Execute this line of code. You can see that from our data frame, we are having a total of 7 columns. The range index says that we have 1,500 entries. So in other words, we can say we have 1,500 rows in our data frame. For the null count, so you can use the null count to determine if your column does have missing values. So you will do this by comparing the range index, the number of entries, as well as the null count for each row. For this data frame, you can see that the column length it's having 14,663 null values. So basically it's missing around 37 values. So we are having missing values in the length column. And also you can get the type of data values in the respective columns. So I'm going to move to the next step, which will be data cleaning. So I want to tackle the issue of missing values. So I'm going to start by modifying the names of the columns. So I want to do away with the underscore and be a little bit descriptive with the names of the columns. So I'm going to be modifying the names of the columns. When modifying these names of the columns, I'm going to be using the rename function. And inside the brackets, I'm going to specify I'm renaming the columns. And then I'm going to use a dictionary where I'll be assigning the key value pairs. For the first column, is genuine. I'm changing to, let's say, genuine. The next column, diagonal. So it will remain the same, but I'll just change the first letter. So I want to start with an uppercase letter. So for the rest of the column names, so like for the height left, so I just removed the underscore and started the first letter with an uppercase letter. When we run this, as you can see, now we have a little changed the names of the columns. So I wanted them to be a little bit descriptive. So that's why I modified those names. The next thing that we are going to be doing is we are going to be dealing with the missing values. We will be using the simple imputer to fill the missing values in the data frame columns with the mean value of that column. The missing values are in the column length. So what we will be doing, we will be finding the mean of the values under the length column, And once we determine the mean, we are going to fill those missing missing spaces with the mean value. I will import the simple imputer class from the scikit-learn. So by this line of code, I will be importing the simple imputer from the scikit-learn. Then we are going to create a simple imputer for filling the missing values with the mean. So the strategy that we will be using will be mean. So I will pass in a parameter, so strategy, and our strategy will be the mean. Since we are targeting the length column, we will be using the imputer to replace any missing value with the mean value of the length column. So with this line of code, this line applies the imputation to the length column. So this the length column, and then apply the imputer strategy, which is we are dealing with the mean, and replaces any missing value with the mean value, this one. And the result, it will be assigned back to the length column. So we are not changing. When I run this, then I'm going to use the isNull function to check if we are still having missing values in the length column. So when I run this, you can see that in the length column, we don't have any missing value. Or if we just cross-check using the info method, you can see that the range index, we're having 1,500 entries. And earlier, we were having 1463 null values in the column length. So after that, we have after imputing using the simple imputer with the strategy mean, we replace those missing values with the mean value in that column. And as you can see, we are having 1,500 null values in the length column. So technically, we have solved the issue with the missing values. Now we can then move on to applying the XGBoost algorithm in fake bills detection. So I will begin by importing the necessary modules as well as the libraries. For the first one, import XGBoost as XGB. So we are using the XGBoost in fake bills detection. And in this analysis, we are focusing on the classification. So we will be using the classifier, the XGB classifier from XGBoost, which is used for the classification tasks. We will be, again, for this analysis, we will be splitting the data sets in the training and the testing sets. By that, we will be using the train test split. In terms of evaluation of our model, we will be using this module. In terms of feature scaling for values in our data frame, we will be using the standard scaler. So that's why we imported this. So we'll be using the confusion matrix, the F1 score, and the classification report. All these are necessary when it comes to determining the model performance. Okay, so I will do away with this. There is also another one. When we look in the column genuine, you can see that we're having categorical values. So we will need to assign these categorical values. We need to assign them numeric values before creating our model. For us to perform that, assign numeric values to the categorical values in the genuine column, we will be using the label encoder. So I will also be importing that module. So we only have one column having categorical values, and that is the genuine column. So we need to use the label encoder module to assign numeric values to these categorical values. So when encoding, so I'll start by first initializing the label encoder. The next step will be encoding the categorical values in the genuine column. So if genuine, so we are targeting the genuine column. We specify genuine, and since we initialize our label encoder, so I'm going to use that label encoder. We fit and transform. By this, as you can see, under the genuine column, instead of the categorical values true and false, we have now assigned numeric values to those categorical values. So the genuine column will be our target variable. So we need to start the process of training our model. When training our model, the first step will be defining the features as well as the target variable. We start with the normal x and y. So for the x, which represent our independent variable, the features include diagonal, height left, height right, lower margin, upper margin, and length. For the y, which is the target variable, so this will be represented by genuine. The next step will be splitting the data into training and testing sets. So earlier on, we said we will be using the train test split module. So then we use the train test split module. So we are going to be splitting the x as well as the y. So the x features and the y features. Then we are going to specify the test size. Our test size, for this case, I'm going to set it at 0.2. So 20% of our data will be used for training, for testing, and I'm going to set the random states. So let's use 42. So this is just the seed value. So that will be the step number 2, where we are splitting the data into training and testing sets. For step number 3, it will involve feature scaling. And when we talk about feature scaling, this is a pre-processing technique that is usually used to standardize or normalize your data. So feature scaling is very important. Sometimes you can have values where some values are of larger magnitude, and when training your model, they may dominate the entire learning process. So, and this can lead to models being biased towards those features, and also it might lead to the model ignoring certain features. So by scaling, we are ensuring that all features are treated equally in terms of their contribution to the model prediction. So there are different ways that can be used for scaling, but for this case, I'm going to use the standardization, which is also known as the Z-score. In standardization, you're going to transform the features so that they have a mean of 0 and a standard deviation of 1. And this will make the data follow a standard normal distribution. We'll just be using the standard scalar module to help us with this standardization process. So we won't be doing the mathematical part of it. So the first thing with feature scaling, I'm going to initialize the standard scalar. Then we're going to fit the scalar on the training data and go on and transform it. And also you're going to transform the testing data using the same standard scalar. That is it. So we are fitting the scalar on the training data and transforming it. So after we are done, we save that in a new variable, xtrain_scaled, just to denote that we have scaled the output that will be stored in this variable. For the testing data, again, we are transforming the xtest. Then we will be saving that in the xtest scaled as a variable. The output from the xtrain_scaled variable, you can see that this will be the values, the new scaled values. So this will be for the xtrain_scaled. And when we look for the new values in the xtest scaled, you can also see that we have applied the standard scalar. We build the XGBoost model. So the first thing when building our model, I will initialize the XGBoost. So XGB classifier. So by this line of code, we are just creating an instance of the XGB classifier class and assigning it to a variable XGB classifier. So the next step will be training the classifier. So by this, we are going to fit the XGBoost classifier on the training data. The XGB classifier dot fit, and we are fitting that to our xtrain data. So we use the xtrain_scaled and the y-train. So with this line of code, what we are doing is that when you call the XGB classifier, you are essentially training the XGB classifier on the training data, so that we use the X-trained data. The model will learn from this data and build a predictive model that we are going to be using in the in the future predictions. And when we execute this cell, as you can see, we are getting the XGB classifier. So by default, these are the hyperparameters that our XGB classifier is using. So we can then move to the next step. So we have trained our classifier. So step 6 will be making predictions on the testing data. So we are going to be applying our classifier to a new set of data. So this we are going to regard this as unseen data to make prediction on the test. So these predictions will be made on the testing set of data. So when we execute that, you can see that we are getting outputs of zeros and ones. So these are the predictions when using our classifier. I'm going to start with the classification report. Okay, so when we run the classification report, you can see we are getting the precision, the recall, the F1 score. But my main focus, I want to focus on the precision. Precision measures the accuracy of the positive predictions made by the model. So for class 0, we are getting a precision of 1. And for class 1, we are getting a precision of 0.99. So in the context of our data, the precision of 1 for class 0 means that when the model is making the predictions, it's making correct or 100%, it's making correct predictions 100% of the time. And similarly, a prediction of 0.99 for class 1 indicates that when the model predicts instances of class 1, it is correct 99% of the time. So basically, you can see that our model is quite accurate. Remember, this is just for practical purposes. In real case or in real examples, you might not necessarily get these high scores, and you might need to go further and perform other types of analysis just to make sure that you are getting good scores. Another model evaluation report, you can get that from the accuracy score. So when we run that, we are getting an accuracy of 0.99, or otherwise we can say an accuracy of 99%. So the accuracy score of 0.99 or 99% means that our classification model is making correct predictions approximately 99% of the time. This is, as you can see, this is a very high accuracy score, indicating that our model is performing very well in terms of classifying instances correctly. And the last one will be the confusion matrix. So we are going to print the confusion matrix. So for the confusion matrix, this is the output. So the confusion matrix, generally it is providing a summary of the performance of the binary classification. And in the confusion matrix, we are getting some values. And these values, generally, the confusion matrix displays the count of the true positive values and the true negative values, as well as the false positive and the false negative predictions of the two classes. And remember, our classes are 0 and 1. So for the true positives, there are 190 instances where the model correctly predicted class 0. So for this confusion matrix, the first vertical line, so 109 and 0, so this will be for class 0, and 1 and 190, this will be for class 1. So for true positive, there are 190 instances where the model correctly predicts class 1. And for the true negatives, there are 109 instances where the model correctly predicts class 0. So 109 for class 0 and 190 for class 1. So those are the correctly predicted instances for both classes. For false positives, there's one instance where the model is incorrectly predicting class 1 value when it should have been for class 0. And when we look for at the false negative, there are 0 instances where the model incorrectly predicts class 0, when it should have been class 1. Okay, so for the false negative, 0. For the false positive, it's 1. So generally from the confusion matrix, you can conclude that the confusion matrix shows the model is performing very well with an almost perfect number or a perfect score of true positive and true negative predictions, and only a small number of false positives. So that's all for today. We have now reached the end of the analysis. Once again, thank you for joining me today. Thank you for your time. And before I sign off, please consider subscribing to the channel. Hit that notification bell so that you never miss any of our video updates. You can also like, comment, and share because we love hearing from you. Once again, thank you. And until next time, see you.